Hi everyone, my name is Nhan Tran from Cornell University, and I'm glad to be here to present Personal Time-Lapse. This is a work with Ethan Yang, Angelique Taylor, and Abe Davis. The human body is constantly changing, and a lot of that change is fast and temporary, like the motion of walking or the waving of arms. This can make it difficult to observe the slower, more subtle changes, such as the growth of hair or the formation and healing of wounds. And this is a problem because tracking these slower changes can tell us a lot of important information about our health. Now, in clinical settings where you have access to the right professional expertise and equipment, there are strategies for standardizing how photographs are taken to address this challenge. But most of the time, the patient is not in the clinic. They are at home, or at work, or at an HCI conference. And the one thing they are likely to have in all of these places is a mobile phone. So what we want to do in this project is something pretty ambitious. That is, to build a mobile application that can help track changes of the body over time outside of the clinical setting as the user goes about their daily lives. And we do this by capturing what we call personal time-lapse, which is a 3D time-lapse of the user's body under consistent conditions that we can use to track growth or healing over time like you see here. Okay, so how did this work? We start by having someone capture a reference observation of the subject under desired conditions. And here, that someone could be the subject themselves or their physician during an initial visit. Then the goal of the app is to help the user reproduce the conditions of this reference observation every time they capture new data. So that over time, repeated capture gives us a time lapse of the subject fixed under these reference conditions. Now, we define 3 types of conditions that we want to help the user control, which we derive from a review of literature on clinical photography. The first and simplest condition is viewpoint, which describes the pose of the camera relative to the subject. Our second condition is the configuration of the subject, which describes its pose relative to itself. This includes things like the angle of various joints, which can have a major impact on what we observe. For example, bending a joint can stretch the skin tighter or looser around the body, which can change the appearance size and shape of the visible wound. And for our final criteria, we want to keep the lighting consistent in each photo. We'll come back to lighting later, but first, it's important to note that these 2 adjustments require a spatial understanding of the scene. This means that to provide guidance, we need to be able to track both the subject and the camera. Unfortunately, existing mobile tracking APIs like ARKit, which rely on sparse visual features, don't work on non-rigid subjects, like body parts that bend or deform. So if you move your fingers or change room, ARKit will stop working, as shown in the left video. Instead, we built a custom tracking system from the ground up based on geometry, which is independent of appearance and robust to small deformations. Adapting the technique to a mobile platform was a substantial engineering effort. However, the method we use is based on existing algorithms in geometry-based tracking that have been successfully utilized in larger devices. So we refer to the paper for algorithmic details. For the purpose of this talk, though, we're going to focus on the interaction design that this tracker allows us to explore. Now we have a way to track our subject, but providing guidance on both viewpoint and configuration is still challenging due to the numerous degrees of freedom involved. Viewpoint alone has 6 degrees of freedom, and configuration adds an unknown number of additional degrees depending on the specific subject. Navigating this high-dimensional space of configuration is actually much harder than it seems. In a formative study, we found that users significantly overestimate their ability to capture consistent observation of their hands. We observed that the result hold under various capture conditions. For more details on the study, please refer to the paper. Furthermore, we searched online and found that the most common type of personal time-lapse is selfie-a-day videos. Interestingly, this aligned with one of our user study findings, that faces are easier to recapture than other body parts. The one instance of someone capturing high-quality personal time-lapse for the other body parts that we can find is from the professional filmmaker named Balin Kolsvarit, who created a time-lapse of his wounded finger healing. This video has been seen by millions of viewers across different video platforms. We reached out to him, and he described his method, which is more similar to what you find in medical photography settings, including using a plasma mold and studio lighting. He reported that it could sometimes take up to 15 minutes to find the right position. Now, let's first focus on the viewpoint, which has a fixed degree of freedom. Since we know what those degrees of freedom are, we can map them to specific visual elements for high precision feedback. For translation in the plane of the camera, we have the moving ring representing the vertical and lateral movement of the camera as it moves side to side or up and down. There's also a blue ring in the center that serves as a reference point that you want to line up with. For rotation, we map it to the motion of a white crosshair, which moves according to the relative orientation of our subject and the reference. A correct orientation is achieved when the white crosshair aligns with the blue reference. Moving to subject configuration, here we don't know how many degrees of freedom the body parts will have ahead of time, so instead of mapping specific degrees of freedom to specific visual elements, we use a color heat map to visualize alignment across the entire image. In this color heat map, we blend it with a reference image where green indicates the optimal distance, blue means too far, and red signals too close. But this color map doesn't just represent the overall depth in the Z direction. It shows the depth differences at each individual pixel between the current and the target pose, highlighting the areas within the subject that require finer adjustment. So for the hand, this could be a slight shift of just one finger. Now, let's see our guidance in action. During capture, the user sees an overlay of the target image blended with our color heat map. Since we can evaluate these capture criteria in real time, we can automatically trigger capture when the target conditions have been met. So to validate our guidance, we conducted a user study that demonstrates substantial improvement in the geometric accuracy of users' ability to return to the same reference view and configuration. We evaluated it with 2 quantitative metrics, as well as user assessment on a Likert scale. For more detail, please see our paper. Okay, if you recall earlier, what we have shown so far addresses our first 2 capture criteria, but we haven't addressed lighting. When we take a photo, we capture the scene lit by light from the environment that we cannot control. And this light is rarely consistent across time and different environments. In fact, the only light that we can control is the light that comes from the phone itself. So what we'd like to do is factor out this uncontrolled environment light and show what the image would look like if it was lit only by the light that we can control. For instance, the flash from the phone. So by capturing both of the images very quickly in the burst and subtracting the environment light, we get an image that's consistently lit by the light we do control. To see everything in action, we examined 2 separate long-term case studies. In the first study, we had a user track the healing of a burn on a hand over 35 days. What we show here is an example of the user capturing an observation using our app. So here's a sequence of data he was able to capture. And we can see that his hand is quite stable in these images, which show that we control the viewpoint and the configuration of each capture pretty well. But the lighting is all over the place because almost every frame is captured in different environment. And since we capture a burst of 2 photos in rapid succession, here are the images with the flash turned on. And this is what the result looked like after taking the difference between these in the linear representation. This let us visualize the subject under consistent lighting conditions, even if it was captured in uncontrolled settings. For our second long-term case study, we had a user track the growth of facial hair after a clean shave, and we have shorter-term results on a variety of other body parts as well. For additional examples, please check out our website. Lastly, we note that while we designed this with healthcare application as a primary focus, our tool is general purpose. We are interested in applying this to other applications like plant science, since it lets you capture controlled observation of non-rigid subjects in field settings. Okay, so to wrap up, We have developed a custom ISV-based tracking system for mobile devices. Our 3-part guidance system significantly improves capture accuracy through controlling viewpoint and subject configuration. We have implemented a novel approach to control lighting in uncontrolled environments. Thank you for your attention. Please check out our paper and the interactive result on mecapture.com.
Hey there. I think this is obviously incredible work. One thing I was curious about yesterday was that this really seems to depend on a well-defined initial template to compare against. I'm just very curious to hear how you think you'd change this setup if there was no sort of best template being measured against, but rather it was just a collection of 16 somewhat similar images. How would you, and maybe you weren't letting the user choose which one was the best one. How would that change your approach, and what issues do you think you'd run into?
Yeah, so that's a great question. So yes, you're right that right now we use the initial image as the reference. But
taken by like a sort of more professional user, not the person who's going to take it in the field.
It could be captured by the user or by the physician.
Yeah.
So we could have like an interface that let the user pick the reference that best demonstrate the initial observation, or they can go to the doctor and then they can work out like what an initial reference could be.
Okay, cool, thank you.
Thank you.
Hello. Seeing as it's mainly used as a medical device right now, and medical adherence to like treatment programs are a pretty big issue, how does it handle missing data, like if they just skip a couple days?
This is a great question. So as mentioned earlier, we designed this intended to be general purpose and not for a specific clinical task. However, I could imagine one feature could be like a reminder. So like, for example, it could like send an alert, hey, you forget to capture at this day on this time. Can you please recapture?
Thank you.